Good afternoon, my dear students. Welcome to online classes of Ahmadiyya International School. So today I am going to start a topic, solid materials. Solid materials. So I am going to do just a part of solid material, and then in future maybe 2-3 days we are going to do the remaining part of solid materials. So we see first under materials we know that we can divide into two parts, solid materials and fluids. Solid materials and fluids. So already we have learned fluids, we have completed. So we are going to learn solid materials. So we see first, when you are starting solid materials, we see what is meant by tension. Tension, T or F. What is tension actually? Tension means when you just take a material and when you apply the force, parallel to the body, and if the length of the material increases, we call as tension. We call that force as tension. We see what is meant by compression, compressive force. Compressive force. We see what is meant by compressive force. The compressive force will be if you just apply a force to a body, and if the body compresses or the length of the body increases, if the length of the body decreases, we call as the force compressive force. The force is known as compressive force. Right. We see what is meant by extension. Extension, we are denoting as delta x. Extension will be when you apply force, the increase in length. Increase in length we call as extension. So we see what is meant by compression. Compression, that's also we denote as delta x. When you apply a compressive force, the material, if it is decrease in length, the decrease in length we call decrease in length we call as compression. Actually, in another way, we can say compression as negative extension. Negative extension. Then I am going to explain a very important law, Hooke's law. Hooke's law. It's a very important law in materials, solid materials. Hooke's law says that if you just take a material, say a piece of wire, just hang from a clamp stand, and when you apply a force, we know the material shows extension. The law says that extension is directly proportional. Extension is directly proportional to the stretching force, or we can say load, or we can say tension, within the limit of proportionality. We later study this definition of limit of proportionality. Extension is directly proportional to the stretching force or load or tension or applied force within the limit of proportionality. So as a equation, F directly proportional to delta x. So we can just write proportional sign, we can put equal and constant, so F equals K delta X. This is the equation which is given in formula sheet, you can directly apply. This K we call stiffness constant, or sometimes if you use a spring, we can say spring constant, or we can say proportionality constant, right. We see now, this is the law, you can see as F increases, delta X also increases. This is Hooke's law, right. We see now the definition of K, definition of stiffness constant, So we can use the equation F equals K delta X. So K will be F over delta X. So you can write, if they ask the definition, you can't directly write the equation. I think you can write the word equation. We can say that stiffness constant will be equal to force divided by extension. Or we can say force per unit extension. We can say force per unit extension. We can say as stiffness constant or spring constant. Then we see units of K, spring constant or stiffness constant, units. So when you are calculating, just write in the units, if K equals F over delta X, you can directly substitute the unit. First we see SI unit of K will be equal to Newton, here meters, so Newton per meters. SI unit of K will be Newton per meters. Then base unit of K will be, Newton will be kg ms minus 2 into m minus 1, m cancels, so base unit will be kg s minus 2. That is the base unit of K. This spring constant, remember students, this K depends on the dimensions of the material. That's very important. K depends on the dimensions of the material, whether it is thin or thick or long or short. K depends. Right. Then we'll see important graph of force against delta X. I'm going to draw a graph force against extension for material. So I can select easy material. Since we are going to learn later a lot of materials, we can use copper. So force Newton, delta X meters, and here the shape of the graph will come like this. You can see that. So then I am going to mark some important points. So here you can see this is, we call L, we call limit of proportionality. Just above the limit of proportionality, there is another important point, elastic limit. And then just above elastic limit, there is another point called yield point. And then at last, the end of the graph, we call breaking point B. Okay? Right. So these 4 points, you should know very well the definitions. So we start one by one. First one, we'll start limit of proportionality. of proportionality. Limit of proportionality. How do you define limit of proportionality? We can say that this is, we can say this is the point up to which material obeys Hooke's law. We can say this is the point up to which material obeys Hooke's law. Or we can say F is directly proportional to delta x. That is up to a certain point, F is directly proportional to delta x, and that is we call limit of proportionality, or L. Right, it's the straight line part, you can see that. Then the second definition will be elastic limit. Elastic limit. So that is, we can say up to point E the material is elastic. Up to E material is elastic, we can say the point up to which when applied force is removed, the material will return to its original dimensions. Or we can say it is the maximum extension where when the force is removed, the material will return to its original length or original dimensions. Yeah, so that is elastic limit. We see third point, yield point. Yield point, that is Y. That is just above the point elastic limit. So since we haven't studied about elastic deformation and plastic deformation, we can just define yield point as the point, we can say the point where, we can say the point when there is a large change in extension, the point when there is a large change in extension for a small change in force, small change in force. When there is a small change in force, there will be a sudden change in extension. When there is a large change, we can say when there is a large or sudden change in extension for a small change in force. Okay? So when you just apply a small force, there will be a large change in extension, that is we call as yield point. Right. Then the last one will be breaking point. Breaking point. Breaking point. We can say breaking point as simple way fracture point. Fracture point. Fracture point. The fracture point, or where the point where the material breaks. The point where the material breaks. When you apply force and go, there will be a point where the material will get fractured and it will break. That is we call breaking point. So then we have learned more important definitions. Now we'll go to just experiment. As experiment, I will give you experiment to investigate Hooke's law. Investigate Hooke's law. Experiment to investigate Hooke's law, or we can say to measure, we can just say to measure K, spring constant. We are going to measure spring constant. Right, we see how we can determine or measure the spring constant. So we can use this type of diagram. We can use a clamp stand with a spring, and then we can attach some slotted masses or weights, and then we can just near to the spring we can keep a meter rule. This is meter rule, and we can use a pointer, so we can easily note down the readings. And here you can see this is the mg weight, and tension will be T, and we know T is equal to mg, and this is a pointer or pin. This is a normal diagram. The meter ruler should be straight or vertical, closer to the spring. This is a spring. We are going to find the stiffness constant of spring. Then what you can do in this experiment, we can just we can say vary the masses, hanging masses, and measure corresponding extension delta x. So vary the masses. You can just start, say you are starting with 100 grams, then 200, 300, like that. You can just do the experiment. So vary the masses and measure corresponding extension. Right. You can make a small table. So you can see here mass kilogram, then corresponding extension delta x, and then force will be mg, it is in Newton. So you can just get many readings, 6 or above, so to plot a graph. Right. Then our equation will be F equals K delta x, it is like y equals mx. We can say plot a graph of force against delta x. We are going to draw a graph, force against delta x. So force will be in y-axis and delta x will be in x-axis, straight line graph through origin. So we can assume that the material not past the elastic limit or limit of proportionality. Then in straight line part we can calculate the gradient. Say this is delta x and this is force. So gradient will be equal to directly k. So k will be equal to F over delta x. So you can find the spring constant. From this experiment you can find the spring constant. So with the help of a diagram, briefly you can explain. Right, so this is the way we are determining k value. You see what is meant by deformation. So deformation means actually a process where change the shape of a material due to the force we call as deformation. Right. Then we see there are two types of deformations we are going to learn. First one, you can say elastic deformation. Elastic deformation will be, we can say that when applied force is removed, the material will return to its original dimensions. Original dimensions. So when applied force is removed, the material regain or will return to its original dimensions. So original dimensions means original, if it is wire is a cylindrical shape, same cross-sectional area and same length when force is removed. That is we call elastic deformation. Right. Then second one I am going to explain plastic deformation. Plastic deformation. So these terms mostly in the papers they are asking, so you should know the definitions. Plastic deformation means that is also a change when applied force is removed. When applied force is removed, after applying the force, when it is removed, the material will not return to its original dimensions. It is permanently stretched. It is permanently stretched. It is permanently stretched. When it is past the elastic limit, it will be permanently stretched. Right. If you just draw the force extension graph, you can see here force, here extension. So the graph will go like this, say as example, force increasing, delta x also increasing. So up to the elastic limit or limit of proportionality, when you apply force and then when you remove the force, the material will return to its original length or shape. So this part you can say as elastic deformation. After passing the elastic limit, say the material have gone to this position, the point I will just denote as x, and then if you remove the force, it will not return to this position, it will return in a different path. You can see how it comes, but it should be parallel to this, and it will, when completely force is removed, you can just see that there will be a permanent extension will be there. That's why we call this part, actually we can say as plastic deformation. Plastic deformation. When you apply force is removed, you can see it will not return to the original position, it will return to some place where there will be a permanent extension. So that is we call plastic deformation, and these two lines will be parallel because the spring constant is a constant value for that. That's why we are going to learn now elastic strain energy. Elastic strain energy. Elastic strain energy. So we just denote this one as E elastic. Elastic strain energy. We see what is meant by elastic strain energy. So when you apply a force to a material, we know the material will extend. So up to the elastic limit, whatever you do work, it will just, what will happen, stored as elastic strain energy. When you do some work by stretching the wire up to elastic limit, what will happen? The energy will be stored as strain energy. We call elastic strain energy. Right. So we'll just take a material, and then when you apply a force, what will happen? We know the material will stretched. So elastic strain energy will be the energy stored due to the work done up to elastic limit. So the work done is equal to elastic strain energy stored. So when you apply force, the material is extending delta x. So when you apply a force, initial force, just before applying the force will be 0, because you can see no extension, no force. When the material extend at this place, the force will be F. Because we know that during this time, not like other work done, here the force is not constant. With the extension, force also vary. So initial extension, initial force is 0, final force is F. Then we have to talk about average force. So average force will be 0 plus F divided by 2. So initial force plus final force divided by 2, and we call as average force. So then I can write work done, or we can say elastic strain energy. Work done or elastic strain energy will be, we can say, average force into extension, or we can say displacement also, we can say average force into displacement. That is the definition of work done. So average force will be here F by 2, displacement will be extension, we can write delta x. So here delta E elastic, or we can say elastic strain energy will be equation, we can write delta E elastic will be equal to half F delta x. This formula is given in formula sheet. Okay, you can see how the equation comes. So work done, whatever the work done will be stored as elastic strain energy, and then that is equal to average force into displacement. And here when do this question, F always should be in Newton, delta x always should be in meters. When they give in centimeters or millimeters, convert into meters, and this will be always joules. Right. So then if you draw a graph, we have done this force against delta x graph. You can see that this is the extension, this is the force, then the area under the graph, you can say area will be equal to, area under the graph will be equal to half delta x into F, half F delta x. In another way, elastic strain energy. You can write delta W or delta E. You can see that how it comes. So area under the graph gives elastic strain energy, gradient gives spring constant. So both you can calculate from this graph. Then we see that this elastic strain energy, when you take delta E elastic is equal to half F delta x, and this is the one just now we got it. And then we know from Hooke's law F equals K delta x. So if you substitute here, you get delta E elastic will be half K delta x into delta x. So it will be delta E elastic will be half K delta x squared. So if you just draw this graph, because sometimes they are asking the shape of this graph. What is the shape of this graph? You can see elastic potential, elastic strain energy and extension. If you draw, the shape will be, you can see when the delta x increases by small amount, delta E will increase by large amount. So, and you can see when the delta x is 0, when the extension is 0, no energy is stored. So it start from here and increase like this. The shape will be a curve. Right. So you should know how to draw these graphs. Then there is another equation delta E equals half F delta x. In some places, if you want to use, you can use, if you join this, if you remove delta x will be F over k, F over k. So, delta x place, if you substitute F over k, you get delta E elastic as half F into F over k. So, delta E elastic will be equal to F squared over 2k. It's another equation which is not given in formula sheet. If they have given the spring constant and F, so you can just work out the elastic strain energy by using this equation. Right, students, we will meet again for the second part of solid materials. That is, I am going to continue with stress, strain, Young modulus and experiments with some calculations, and we will have that class as soon as possible. So, until that, goodbye. Thank you.